Hi guys, in this video I want to talk to you about rotational kinetic energy and applying it to the most common scenario this concept is applied to in AP Physics 1. I don't know why, but College Board is really obsessed with racing random objects down ramps. So in this case I have a sphere, a hoop, and a box for you. And real quick, which one's gonna reach down first? You can use our old friend rotational Newton's second law, the one that accelerates the one with the highest rotational inertia is the one that's going to accelerate the least, rotationally wise, and it's going to take the longest to kind of roll down the ramp. So if you're comparing a hoop with all of its mass on the outside versus a sphere with some of the mass spread out not as far as the outside radius, then the sphere has the lower rotational inertia. We'd expect it to kind of go down first. Whereas a box, it's not rotating at all, so it has the lowest rotational inertia. It's not rotating, so it would reach first. So hopefully you saw that, or I can show you a video, whatever. We want to just analyze this now with energy. So in terms of energy, hopefully this is, again, the gist of this. You want to think in terms of the energy conservation equation. I'm going to put the Earth and my object in my, let's say, the incline in my system. Where does the energy start initially? They all start at rest, I'm assuming. So it starts off as gravitational, and in the end, suppose my height 0 is here. The gravitational is 0. There's going to be some amount of kinetic because these things are moving linearly, like their center of mass is in motion. But there's also going to be some amount of rotational kinetic energy. And I want to just unpack this energy conservation equation a little bit, and hopefully that'll shed some light on what's going on here. So Eg at A is equal to Ek at B plus Ek rotational at B. This is just mgh 1/2 mv squared plus 1/2 I omega squared. So the equations for all of these are going to be the same, but the coefficient for I is going to be different. Just recall I is proportional to some constant times mr squared. So I'm going to just put in C, mv squared plus 1/2 CMR squared, omega squared. And I basically want to just relate this to the kinetic energy because I think it's easier to see it that way. So 1/2 mv squared plus 1/2 c mv squared. Just remember r times omega equals v. So this right here is v squared. So I think this is a good place to kind of just look at it. Let's say I have 100 joules of gravitational energy. If this C was a 1, then what this is saying is that half of the energy would be in this kinetic energy due to the center of mass, and half of it would be due to the rotation of the object. What would happen if C was 0? Well, then this term would go away, and all we would have is the linear kinetic energy. That's what we've been doing this whole time. That's what describes this box. It's not rotating. Its rotational inertia, like, it's not rotating. So this term is just 0. I don't want to say that it has no rotational inertia. It's just, in this case, it's not rotating. Theoretically, I could rotate a box. So it's not right to say that the coefficient is 0, but if something's not rotating, this term goes away. And this, what I'm trying to suggest is the smaller and smaller this coefficient is, the less and less energy is stored in rotation, the more energy is stored in the linear motion of the object. But the larger and larger the coefficient for the rotational inertia, the more energy is stored in just getting the object to rotate. So that's kind of what's going on here. You can say that, and just to bring it all home, the box isn't rotating at all. So all of the energy is in EK rotation, in the kinetic energy due to the motion of the center of mass. That's for the box. For the sphere, some energy is stored in the rotation, but a lot of it is in the linear motion of the center of mass. That's why it would reach first, because it's covering that linear distance in less time. It has a higher average speed. That's why it has that more kinetic energy. Whereas this hoop is kind of as slow as you can get, as much energy in the rotation as possible. Those coefficients don't go above 1. Off the top of my head, I don't think they go above 1 on the table. That's not really an important fact, though. The idea is the higher this constant, the more energy stored in rotation, the slower it'll reach that ramp. So that's sort of the energy analysis here, and you should definitely be prepared to think through this on an AP question. Hope that was helpful. Take care.